As a continuation of our discussion of various synthetic aspects of SN and E reactions, I'd like to talk about some SN2 and E2 reactions with a variety of different nucleophiles. In particular, when you have strong bases, E2 reactions often occur even when you want SN2. So I have here two lists of nucleophiles, the lists from the Karty tables and Stromanis tables of good nucleophiles here in the red, and I have here a list of some nucleophiles that we've seen. For example, halides can act as nucleophiles because they're such weak bases. They can work in either SN1 or SN2. Water, methanol, ethanol, alcohols, very weak bases work in SN1 or SN2. I have the carboxylate, the conjugate base of carboxylic acid here, and it is actually a very weak nucleophile. Very few things that react with it through SN2. I will show a specific example later in this video. Cyanide ion, pretty weak base. Neutral amines, relatively weak base, but good nucleophile. In fact, in terms of good nucleophiles, or they are the best neutral nucleophiles. And then we start into our stronger bases. Hydroxide ion, strong enough nucleophile, you'll only see it in SN2. It's also a good base for E2. Because of its small size, it works pretty well for methyl primaries and unhindered secondary SN2 reactions, and secondaries in E2 with a hydroxide if it was hot and you had a protic solvent, things that would slow down SN2 or speed up E2. So again, your weaker base nucleophiles can work in either SN1 or SN2 reaction conditions because they can be present in the presence of an acid. As you get to your stronger base nucleophiles, SN2 is the only possibility. So for example, the neutral amines and hydroxide ions work well for SN2s and will work with methyl primary and secondaries, assuming the other reaction conditions occurred. So as we get to the stronger base nucleophiles, such as alkoxide ion, enolate ion, and the conjugate base of an alkyne, you'll find these are strong enough bases that they will do SN2, but only with methylene primaries and unhindered primaries at that. When you get more hindered than that, E2 will take over, particularly for secondaries and tertiaries. And that is simply because the base strength starts to outweigh the nucleophilicity of these groups. Finally, we have a set of strong bases, our strongest bases, and these tend to act only as bases for regular proton transfer reactions or for E2 eliminations. So let's look at some examples in which these different base strengths and these different nucleophiles are active. I'm going to spend very little time on the top set, the SN1, SN2 ones, since you've seen those extensively, with the exception of the carboxylate ion. And the carboxylate ion is interesting in that it's a very weak nucleophile, but it will react with particularly active electrophiles. One example of that is the diazomethane reaction. In the diazomethane reaction, we take a neutral carboxylic acid and we react it with this special reagent, diazomethane. Diazomethane, if you write it out, can be written as two good Lewis forms, one of which shows that the carbon on the end has a basic character. And in fact, it is this position that reacts with the acidic carboxylic acid in an acid-base reaction. This creates a carboxylate anion and a methyl diazonium cation, something with a methyl group, very unhindered, excellent electrophile, attached to a diazo group that can leave as a neutral N2. And that's exactly what happens. In our second step, we get a nucleophilic substitution, our weak nucleophile acting with our diazonium methyl group to give us our methyl ester and nitrogen gas. The next special consideration has to do with the ammonia and amines acting as nucleophiles. Ammonia and primary, secondary, and tertiary amines are all quite nucleophilic. Even though the tertiary amine is more hindered than the secondary or primary, it does have more carbon groups donating electron density into the nitrogen center, and usually leads to multiple alkylation. And so, for example, if we start off with ammonia, we add an excess of a good electrophile like methyl bromide. We find first we get an SN2 reaction in which the amine reacts with the methyl bromide, kicking out the bromine to make methyl ammonium. Then some base in solution, such as another ammonia molecule, can take off the extra H, giving us a primary amine. But this primary amine is also nucleophilic, more so than the original ammonia because of the electron donating group of the methyl, so it can do a second SN2 followed by a second acid-base reaction and make a secondary amine, which can alkylate a third time, do a third acid-base reaction, creating a new nucleophile which can alkylate a fourth time to give an ammonium ion. In general, it is not synthetically useful to do direct SN2 reactions with amines or ammonia unless you have a large excess of one or the other. In the case of having excess electrophile, you end up adding alkyl groups onto all possible positions until all the hydrogens have been replaced and we make a tetraalkyl ammonium ion. In the case of excess amine or ammonia, you only alkylate once, making your monosubstituted product. There is no practical way with direct SN2 reaction to add 2 or 3 alkyl groups. Next, I want to focus on these stronger base nucleophiles, in particular enolate ions, alkoxide ions, acetylide ions. All of them can make SN2 reactions with unhindered methyl and primary substrates, and two of them, the enolate ions and the alkylide ions, make new carbon-carbon bonds. The third, alkoxide ions, make ethers, and each of these has special synthetic considerations. So, for example, in order to make the CC triple bonded anion, the alkylide anion, you would need to do an acid-base reaction with a base that's stronger than the base you're going to create. So in this case, we start off with sodium hydride as a common base used for this reaction. We do an acid-base reaction, create our alkylide ion, which can then do our SN2 reaction to give us our alkyne product. There are limitations to this, however. If I try to do it with a secondary alkyl halide, for example, a secondary alkyl bromide here, if I do my SN2 reaction, I find I get exclusively elimination product, where we remove this hydrogen in the bromine and made it pi bond, and not the desired substitution product. Again, that's because this base, it's a stronger base than it is a nucleophile, not allowing SN2 to happen at the secondary center. A second example of using these nucleophiles is given a formal name called Williamson ether synthesis. It involves alkoxide ions as nucleophiles in SN2 reactions, and to make the alkoxide ion, again, we use a strong base like sodium hydride to remove the acidic hydrogen, make an alkoxide ion, do an SN2, and make our ether product. However, just like we saw with the alkylide ion synthesis, if we have an alkoxide ion reacting at a secondary site, the hindrance is going to slow down SN2 and the base strength is so high that we're going to do E2 instead. And we would get an elimination product, not an ether, if we chose a secondary or even a tertiary substrate. One synthetic example of Williamson ether synthesis that often is a little confusing for students is when we do an intramolecular, that's within the molecule, Williamson ether synthesis. This comes about when you have an alcohol group and a halide at a primary position on the same molecule separated by either 4 or 5 carbon atoms. And how this works is that your alcohol will react with your strong base NaH to make the alkoxide ion, and rather than waiting till it runs into another molecule, it will reach around, much like a belt buckling or a necklace buckling, and do an SN2 reaction right within its own molecule. And when it does so, it creates a ring. In general, 5- and 6-membered rings are the most stable, and intramolecular reactions will be rapid if you can create 5- or 6-membered rings. Enolate ions likewise form strong bases. When you have a carbonyl with an alpha hydrogen atom, that is, you have a strong base like lithium diisopropyl amide, strong bulky base, and it has two large isopropyl groups. It will pull off the hydrogen in the alpha position, creating a resonance stabilized enolate ion, like so, which has nucleophilic character on this alpha carbon. The alpha carbon can then act as a nucleophile towards SN2 reactions, as long as the substrate is primary or methyl, and we can create new carbon-carbon bonds. and elongate the chain. In this chapter, we also see how enols, which were introduced a while back with acid-base reactions, can act as nucleophiles. As a reminder, under acidic conditions, an enol can form first by an acid-base reaction to protonate the carbonyl, followed by a base in solution, neutralizing the enolate ion to make an enol. Under basic conditions, the acid-base reaction happens first, followed by a protonation. These enols are very weak nucleophiles, being neutral, and react primarily with halogens. In addition to our stronger bases being able to form SN2 and E2 products, we have one final example of an E2 elimination. And that is if we have a vinyl halide. This is the one time where we've seen an sp2 carbon attached to a leaving group. And we treat it with the very strong base and a mid ion, NH2- or NR2-. We can get a second elimination to make an alkyne, and this is in fact the standard way in which we make alkynes. Our very strong base can pull off a hydrogen, create a second pi bond, kick out a halogen, and create a triple bond. This is, again, the common way to make alkynes.